constitutional. There's one carbon in between, right? Up, down, up.
They're both the same, but this one is trans, this one is also trans. They're both trans, they're both the same in number wise and
But they don't have asymmetry, so.
Yeah.
they,
So they don't have symmetry, so we still have to do the whole thing.
why don't they have symmetry?
Because even this, right?
Yeah.
If you even put it like this, like there's one, it's not symmetrical. Does that make sense?
Oh, you meant as in like,
If this OH was here, it would be.
what do you mean by symmetrical? Because if, between the two atoms or the molecule itself, because the molecule itself has symmetry. If you split the molecule this way, it's symmetrical within molecules.
This one?
Yeah.
But then the right side would be the same as the left if you cut it straight down.
No, because if I go
So
this
it has,
way, right?
it has to be, it has to
This
be
one,
within.
this side has an OH, this side doesn't.
Right, but if you look at it from a, okay, so this is what I think I'm failing to understand is you have to treat it as the way that it's placed on paper, because that molecule, if you rotate it,
Even if I rotate it, this OH isn't the same number of carbons away.
if
on
you
both
if you
sides.
rotate that molecule and it goes like this, and the OH is perfectly in front of you, and you split it through that,
No, even if I rotate it, like, there's 6 carbons, right?
right?
And the carboxylic acid and the OH aren't evenly.
Not in the second dimension. You rotate it in the third dimension.
What do you mean?
So if we create a molecule that's like that, and then it has a split on this side, right? And this is what we're talking about, right? If you look at it this way, you cannot make it dimensionally symmetrical. But if you flip it like this, you can.
Rotating it is like to view it a different way, but symmetry itself, like, it has to be, like, imposable.
Like you could place it on top
Yeah.
of each other.
Like,
That's
you can
what-
fold it in half, kind of.
So we do treat it the way that it's given in 2 dimensions.
I mean, yeah.
Okay.
This carbon is missing something, right? The hydrogen. This one is also missing a hydrogen. Oh, by the way, if it has a group on a dash, the hydrogen is going to be on the wedge. If it's on a wedge, hydrogen is going to be on the dash. Same for this one, right? But for cyclohexanes, we do, if it's equatorial, axial hydrogen.
Oh wait, there's the whole trans.
Yeah, so it can't be diastereomers.
Oh.
So we're choosing between, and the enantiomers are the same. Now we're going to identify the centers. So that's one, that's another. Keep it consistent.
Aren't they the same molecule?
Okay. Let's start with
Mhm.
this one.
Mhm.
So carboxylic acid will get 1. And then for these we have CH2s. But after you pass these 2 CH2s, this one's next to one with an OH, and this one has another CH2. So this will be 2. This will be 3, and hydrogen always 4, right? Same thing for this one. OH or O will be 1. And then which is clockwise, but the hydrogen's on a wedge, so we're gonna change it to an S. 1 to 2 to 3 counterclockwise, S. Hydrogen's on a dash though, so we don't change it. Same for this one.
So is it an SS or do we, it just stays as an S?
This one is SS.
Oh, okay.
We started with this one, so 1 to 2 to 3, clockwise, R. Down, away, so don't have to change that. This one, 1 to 2 to 3, counterclockwise, up towards, so we're gonna change this to R. R. What is this?
Enantiomer.
Sure, I don't know.
I have a question. I got so confused as the numbers as one. I know that hydrogen has to be 4, but for the 2 and the 3 in both sides. So in the first, like, in CH2, where you put,
Yeah.
and then the other side CH2 as well. So which one would you consider,
You go to the next carbon down, and in this case, the one with the 2 has the oxygen, which is the tiebreaker.
And the other one only has C's attached.
So it's not
Oh, sorry,
actually
H is
this.
attached.
Well,
So basically, since they're both attached to CH2s, they don't, then you go to the next level.
yeah.
And the next level is that other C that you're gonna talk about anyway later. And that C is attached to O, C is attached to an H, C is attached. So that beats out a lone C that's attached to just H's and another C.
So this CH2, so from this chiral center, there's a CH2 here and there's a CH2 here, right? They're both the same, so we keep going down. This CH2 is with another CH2. This CH2 is with the next chiral center that has an OH and all of that, right? So this one's gonna be higher priority because of that reason.
so CH2 is gonna be 2?
The one in the-
Yeah, so this CH2 is gonna be 2, and this one's gonna be 3.
Okay. So we don't count, like, when we do one chiral center, we don't count the other chiral center. We can omit the chiral
No, you can count the other chiral center. It's about,
Well, because it's, I think, because we're still counting that CH2, the first CH2 has a 2, right? Another 2.
yeah.
We're not.
Comparing.
You do the same thing with the other two.
This one's higher priority because it's attached to the chiral center, and this one's just attached to another CH2. Yeah.
Would it be possible for you to number the second one again, but like one at a time?
This one?
Yeah.
Yeah, I can do this. So for this center, also this is the same. So this is CH2, right? All of these are down. So it's the same here, right? So carboxylic acid will be 1. There's a hydrogen that'll be 4. And then we're deciding between this CH2 that's again next to the chiral center and this CH2 that's again next to another CH2.
So we would choose the one next to the chiral center.
Exactly. So this will be 2 and this is 3. And the same for this one. O will be 1, hydrogen 4. And then we're deciding between this one and this one. Oh, I should not be first.
When we're numbering, do you recommend color coding? Because sometimes we get like when I'm writing on paper, I confuse which one is for Carol's answer.
I mean, for practice, I would say color coding. I don't know. Are you allowed to bring colored pencil?
Yeah,
Okay, yeah, then yeah. I think I just worked with pencil and I would do like, I would bubble in for one chiral center and leave it empty for the other. But yeah, color coding would definitely help.
So for this one, since it doesn't have, the second one, like a wedge or dash, how would we?
Oh yeah, so for cyclohexanes, we said downward means away and upward is toward. So you can imagine this being on a dash, this being on a wedge.
If I take a picture of you.
So number two is in the same position for both, right?
Same position.
This is for the two and me, for the second hexane.
So,
Oh yeah.
So it's the same.
Yeah, so this is this, this is this.
so they're not the same molecule?
They're
Or-
not the same molecule. The same molecule would be if it was SSSS.
Right. So what would be the difference between the two?
So the assignments we got for this
Mhm.
would have been the same exact as this.
No, I know that validates it. I'm saying what is the difference between them, as in like one makes it not the same molecule if they look the same, like
But
that.
we found out that their configuration is completely like opposite of each other, like direct opposites. Like it's, SS becomes RR, right? So that means they're enantiomers, which by definition they are mirror images of each other that can't be superimposed on top of each other. And this is
Oh.
really important in drugs because you want things to
Oh, yeah.
connect a certain way, right?
Right. Okay, that makes sense. So they look basically exactly the same, but they are mirror images. They,
Yeah,
okay.
left hand, right hand.
Right.
I think a famous example of that was they were trying to make an anti-nausea medication for pregnant women, but because it was different configurations, it ended up causing infertility. So it can be really.
What the heck? So simple, yeah, it's kind of difficult to grasp as if you look at it from a mirror perspective, then it would be basically the same thing if you just would turn it 180 degrees. 180? No, it would be a 360 degree on a three-dimensional plane. Should be the same.
He said it's tricky. He's always just practice. Because he said
Yeah.
it's complicated.
They were, of course, kind of complicated.
So we're given this bond line and Fisher. This Fisher we can easily convert this way, like that. And then this one, I just retrace. Oh, sorry, missing image. carbon with Cl. 3. This one is carbon, 2 H's carbon, carbon, 3 H's. That's 1 to 2 to 3 clockwise. Lowest on a wedge, so S. First letter. And then for this chiral center, chlorine will be 1, 2, 3, hydrogen's 4. So 1 to 2 to 3, we're going this way, counterclockwise. H is on the wedge, so R. So this one's SR. And the same thing for this one. Start with this one. OH. Counter. 4 bits away, so you don't have to change this, right?
BCl.
And this center was, you said 1, 2, 3, 4. 1, 2, 3,
4th is a wedge.
4 is wedge. So SR, SR, they're the same.
Nice. Study that.
This one took a lot of practice for me to understand.
Can I take a picture?
Which one? This one that you just did?
Can I take a picture?
Oh, sorry. I have to get better. Yes.
Will this be on the Excel sheet?
Yeah, I'll upload the slides after.
Oh my goodness.
Also, I'm covering some of the like more trickier ones.
Oh, nice.
Yeah. So hopefully, the other practice isn't too bad.
Thank you.
We'll do one more block.
I'm gonna try to see if I can post that thing on